Okay, so just with the craziness of today, decided we could just as easy have this last part of equilibrium. Well, we're not going to be done with equilibrium by the podcast. So page 21, and I wanted you to read in chapter 16, and hopefully you saw it's not something brand new. It's still equilibrium. We're still going to calculate Q. We still have K. We're just being a little bit more specific about what kind of K. So when you see a KSP, SP just stands for solubility product. This is just telling you if something is going to dissolve or not. So back when we first looked at solubility rules, and I said you just need to know group 1s, ammonium nitrates, and acetates, and said don't worry, they will let you know if something is going to be a precipitate. Well, this is how they're going to let you know. They're going to give you a KSP. So you can tell it's a KSP problem because it's always going to be a solid, look at your clues, going to 2 aqueous. So you're just talking about how is the solid going to dissolve. Now, I said you do not have to write equations. You don't have to write equations. This is your exception because it's not really writing an equation. It's not a chemical reaction. You have to show how that solid is dissolving. You will, I have seen those show up. And this is, again, let's look at the key things. So you're going to have states. So states do matter. Okay, but more importantly than states, charges. Because you're all about how many ions make it into solution. So kind of we could picture it as like, I know this doesn't make sense, but like how full is that beaker with ions? So if something is not very soluble, you're not going to get a lot of ions. So you have to be able to write the solid. Now if it's a KSP, you need the double arrow, and you're going to have to make sure you have the charges correct because it's not silver going to chlorine. It's not a decomposition reaction. It's actually just a dissolving. So look at your KSP. It's just going to be the products. We don't use reactants. You'll never, ever, ever have reactants in a KSP because the reactants are always just going to be the solid. So look at down here, and you have this one in your packet. So if I have silver carbonate, is this going to go? Is it dissolving? Now I've forgotten the states. This would be aqueous and aqueous. You should know silver is a +1. And because silver is a +1, it took 2 of them, that's how you knew carbonate was a -2. So in this case, if you write the KSP, don't forget coefficients become exponents. Nothing has changed. It's just one specific type of equilibrium. Let's try another one. Lead bromide. Write the reaction for the dissolving of lead bromide. So we know bromine is a -1. It doesn't matter the order that you write these, but it took 2 bromines, so that's how I know that lead was a +2 and 2 bromides. That would be the reaction or the equation for the dissolving of lead bromide. You will be expected to write these. Don't forget the charges. Don't forget the states. Okay, they will give you these KSPs, and so just recognize what they mean. So the smaller the KSP, look at the exponents, the smaller the KSP, the less soluble it's going to be. This is how in pre-AP you had your solubility tables, and I don't know if you remember in a lab there was sometimes you saw a precipitate when the paper said you shouldn't. There's a few of these that were pretty close to the cutoff, whatever they decided was the cutoff to say is insoluble. So some of these were slightly soluble. So look in this first group here. Which compound is the least soluble in water? Look at aluminum hydroxide. Look at how small that is. Very, very, very few ions. So you have very, very few products. So that means very few ions make it to solution. The most soluble would be silver bromate, but this still is not very soluble. Okay, look at down this one. So lithium actually here is actually fairly soluble compared to over here. Zinc sulfide is pretty insoluble. Now another question could be which would have the most. Look at this one. Let's keep everything. So let's compare here, here, here. Okay, I'm just looking at those three silvers. So which of them would have the, if it's all saturated, which one would have the most silver ions in solution? So you just look at the solubilities. Okay, silver chloride has the highest or the lowest solubility. Try to think of how the best way to say this. It's the most soluble, probably be the easiest, even though it's not very soluble. Comparatively, it's the most soluble. Therefore, it would have the highest concentration of silver ions. Silver iodide is the least soluble, so therefore it would have the smallest concentration of silver ions. Those are common type of multiple choice concept questions looking at the solubility charts for KSP. So what the KSP can tell me then, those vocab words from pre-AP, saturated, unsaturated, precipitate, this is where we're going to apply them and kind of put a quantitative number with them. We will not have supersaturated, okay? Sorry, no supersaturated. It's just going to either be saturated, you can dissolve more, or you will not see a solid, or it is saturated, and if it's saturated, no more ions can go into solution, therefore a precipitate will form. So guess what? We are calculating Q. So I think in the notes, if you look at on page 21, this is kind of written in words that you'd make sure that you write down what it's doing, but the reality is this is what you're just doing, what you've already done. You're calculating Q. And if you remember that Q is the amount of ions, so if Q is bigger than what the solubility product is, that means there's too many ions to go into solution, therefore you're going to see a precipitate. If Q is smaller than K, then you can still have more ions in solution, therefore no precipitate will form. PPT, precipitate. Shorthand. One other thing about a saturated solution. Remember, saturated means they're solid. You're going to see solid. That's how you know it's saturated. You have a beaker. The bottom of the beaker, there's a little bit of solid. That means it was saturated. That's a pretty beaker. So what if I cut the volume in half? If it's still saturated, you're going to have the same number of ions. Well, what if I double the volume? As long as it still is saturated. So that's like a key word you're looking for in the problem. As long as the beaker is still saturated or there's still visible solid at the bottom of the beaker, your concentration of ions stays the same. Because remember, concentration is moles over liters. So yes, more moles, if you double the volume, then you're going to have more moles in solution, absolutely. But you're also doubling the volume, so these are going to increase by the same ratio. So therefore, if I have twice the amount that dissolved, I had twice the volume. Oh, concentration doesn't change. So as long as it stays saturated, saturated means that KSP, now again, it's going to always be usually, that makes sense. It's at 25 degrees Celsius or 298 K, because most KSP tables, that's the temperature. But equilibrium shifts, Le Chatelier, same thing can work. If it's an exothermic, you heat it up. That's not going to help the dissolving. It's actually going to shift it to the left. If it's endothermic, which most are, but not all, if it's endothermic, then you add heat. You should increase the solubility. Okay, we have 4 common problems that you're going to see. So we're just going to kind of work an example of each. So one's going to be find given molar solubility. Okay, Guess what? X is molar solubility. It's just a fancy word for what you've already been solving. So we're just going to be doing some rice tables. Now again, I think the book might do like a fancy S. It's X. Molar solubility is X. So if they give you the molar solubility or tell you the concentration of ions in solution when it's saturated, you can find Ksp. So then you can go backwards. If they find Ksp, you could find out what's the concentration of the ions in solution. We have a new problem here. It's going to be a common ion problem. So really it's putting the math to Le Chatelier. And then the question, hey, is it going to make a precipitate? What's this going to do? Let's calculate Q. Okay, so our first example. So the molar solubility of silver sulfate is 1.5 times 10 to the negative 2. Calculate the solubility product of the salt. Solubility product, Ksp. Get used to that vocab. What is the solubility product? Solubility product, Sp. Ksp is what it's looking for. Okay, so your reaction. Should have made you do this. Next time I will. So silver sulfate, somewhere they're going to give you that the formula. So look at your reaction. You will have to write this many times, maybe not many times on the same test, but look what you have. 2 silvers. So everything is not going to be X and just X. So really pay attention and make sure you write the reaction correctly. So I gave it to you in molarity. Okay, we don't have any ions because it's just in distilled water. Look at your change though. Really, we don't even need to worry about this minus X, other than if it just kind of helps you to look at the stoichiometry. We want to know how much of this is changing. I know it's not in my equilibrium. Okay, you're forming this as a 2X. So this is where you have to be careful with the Ksp and just X. And then notice we don't change it, we don't matter at equilibrium. This is just helping with our stoichiometry. So at equilibrium, molar solubility, this is X. So to find what it is at equilibrium, it was just 2 times that value. And your sulfate is just 1.5 times 10 to the negative 2. Technically, did you have to do a rice table to look at this? Probably not. But sometimes, again, until you've worked more problems, it helps. Next step, you write the solubility equation. Okay, that's why I just kind of stepped out what I did. So here's my solubility equation. So now you just plug in at equilibrium. Don't forget the squares. And then you can find your Ksp. Again, no units on the K. Any of the big K's, not little k's, big K's, we don't have units. So if it says this is the solubility, this is the solubility, they're giving you X. That's how you can find the Ksp. Okay, notice this time I want to find molar solubility. What is the solubility? They may not always have the word molar. If they just ask me what's the solubility or what is the concentration of the ions, they're going to give you an X. Then, excuse me, a Ksp. You're solving for X. Okay, look at this one with calcium phosphate. So we know calcium phosphate, again, they're going to give you this formula. You could write this equation starting from just the compound. You should know calcium's a +2 because it's in period 2 or group 2. And so since it took 3 calciums, that's how you knew your phosphate was a -3. So look when we do our rice this time. Again, 3x, 2x. Some of you might see it without a rice table. You do not have to do the rice table. If it helps you, you use it. If not, you don't. So now it's plugging in. This is why I like the rice table, because it's very clear of what you have to plug in. Now this is where you have to be careful with your algebra, because I've got, plug in your Ksp, and so now I've got 3x cubed times 2x squared. So 3x cubed, 3 squared is 9. 9 times 3 is 27x cubed. 2 squared is 4x squared. 27 times 4 is how I got 108, x to the 5th. So now I'm going to divide by 108. That's how I got 1.2. Just now we have to do our algebra. And so now I have to take the 5th root. And remember we said that if you're taking the 5th root on your calculator, that's the same as 1/5. So you could take 1.1 times 10 to the negative 28 using your exponential button. So it should look like this on most calculators, negative 28, and then you can raise it to the 1/5 power. So I would definitely be practicing on the calculator you're going to use on the test, because not everything is always going to be a square root when we have the KSP problems. Okay, third example. What is the molar solubility, or what's just the solubility of lead iodide in a 0.05 molar solution of sodium iodide? This is called a common ion problem. I know that because I'm not in water. So you're not in distilled water anymore. Now let's look at lead 2 iodide. I don't know why I put it in parentheses. So write your equation. Lead plus 2 iodides. This is like a Le Chatelier, but we're going to actually put math to it. So what if you dump in some sodium iodide? Well, sodium iodide means you're adding more iodide. If you dump in more iodide, you should expect to see the reaction shift to the left. We should see more solid forming. So this number that we're calculating should be smaller than what it normally is. So let's look at how it looks different on a rice table, and it's called a common ion. So we have our lead iodide. Again, we know these are solid, these are aqueous, because that's the only thing I'm going to use in my KSP. Notice the difference now in the initial. Instead of 0 over here for the product, you already have some iodide ions in those beakers, in that beaker. So this time, when you have your change, that won't change. I guess this doesn't need it this time, but we have our 2. But your equilibrium, that's where you are going to see a little bit of the difference. Okay, plug it into your KSP value. Always write the expression. Again, that's probably going to be question A. Now, let's look at, do we have to do a quadratic? Remember, the answer is no. No, you're not. Look at this KSP. This KSP is pretty gosh darn small. So what it's saying, that this little amount that might dissolve is really not going to add much compared to what it started with. It's less than 5%. So therefore you can say, oh yeah, we get to neglect. KSP is so small, we can neglect. So now it's turned into a much easier algebra problem. Remember, you do not do the quadratic on the AP test or on my test. So X is the concentration. Now here's where it's probably going to be more reasonable. Here's that somewhere they may have said you calculated this earlier, and it's like, okay, does that make sense? Look at this. So in pure water, look at this solubility. 1.5 times 10 to the negative third was able to dissolve. So much less was able to dissolve. So that's proving that yes, it shifted to the left. Now, what also sometimes is, instead of just saying molar solubility, it might say, what is the concentration of the lead ions? Remember, that's just X. So this would just be, the concentration of lead ions would be 5.6 times 10 to the negative 6th. So know what that X means, and that is where doing a rice table can definitely help. Okay, last type of problem. It's going to say, hey, I'm going to mix some things. Will a precipitate form. This is where you used to just grab out your solubility rules and use the back of the periodic table. We don't get that anymore. Your back of the periodic table problem is going to be, will you make a precipitate? If I do a reaction, are you going to see a solid form? Notice in your notes, they gave you the piece of information that would have to be provided. What is the KSP? These take a little bit more work. I hope that's the right KSP. I'm trying to see on my notes. What you're going to have to do, typically this won't be one great big problem like this. You would have worked it out in other ways. So what you're looking at, let's see the reaction. So barium chloride, it's a double replacement, K₂SO4. I know that I'm making barium sulfate. Okay, they gave that to me in some kind of reaction, but I don't care about that. They're not going to ask you to write this reaction, the balanced double replacement. This is the reaction that you could be responsible, and it's not really technically the reaction, it's just showing how it dissolves. It's your KSP. That you're going to be responsible. And you don't even know that barium sulfate is the likely precipitate. They now will tell you it's the precipitate because they're going to give you the KSP for the barium sulfate. So the problem is then we are going to have to get your barium ions and your sulfate. It's the only way to calculate Q, because we're going to calculate Q is still the concentration of barium times the concentration of sulfate. And we're going to get that answer and compare it to our K to be able to answer, is it going to make a precipitate? So the problem is you have to kind of go back and go, okay, what is providing, where's the barium coming from? So the barium is coming from the barium chloride. So it is concentration, so we do need moles. So moles is molarity times liters. So I know I have 0.008 moles of barium. However, this is where you have to be really, really careful. Look at your volume. You're adding 200 milliliters now to 600 milliliters. So volume is going to be 800 milliliters or 0.8 liters. So you have to take moles. Remember, we do rice and you do KSP. It has to be molarity. So there's your concentration of barium ions. So where's the sulfate coming from? The sulfate is coming from potassium sulfate. So you have to do the same thing. Figure out how many moles of sulfate, and it's just a 1-to-1, so that's why when you know moles of potassium sulfate, you know your sulfates. But again, it's in the liters, so you have to divide it by 0.8 to get concentration. Now I can plug it into my Q. And again, I didn't look this up. Now on some of the problems, you might have to look up KSPs because the book is not very good about putting it in the problem. So this I gave you. They're going to give it to you because obviously you don't have somewhere to look it up. So now we're going to calculate Q. So just plug in these values to calculate your Q. So now compare Q to your K. This Q is much larger than K. So therefore, you're going to say, yes, a precipitate will form. A precipitate's going to form because Q is larger than K. Now, a nice little shortcut that they do a lot of times when they do these kind of reactions is they do equal volumes of the solutions. So if I had just 400 milliliters of each, remember if you double the volume, you're going to cut the concentration in half. So it would be nice, and this happens a lot of times on multiple choice or something when they're making the math a little easier, that if you see that you have equal volumes of both of the reactants, the concentration of the ions in solution will be cut in half. Just a little bit of a shortcut. Okay, so to practice, I just want you working on the first page of problems, which is only, I think, 3. And I want you to have a nice break, but I also know that you do have a lab that you could be working on. I also will probably put a quizzy that you could be working on just to keep you fresh, because you don't want to take an entire week off of AP Chemistry, because you do have a test when you come back on Wednesday. So I will see most of you tomorrow, but make sure that you ask any questions. We still have a lot of practicing of this, but hopefully you see it's nothing new and scary.